Right. The plan is that we will try to go through 3.7 and 3.8 for the first hour, and we will continue the remaining subtopic 3.9 until 3.12 in the second hour. Right. With regard to Stirling and Ericsson cycles, there are two other cycles apart from the diesel and the what is it called? The Otto cycle that involve an isothermal heat addition process at the temperature high TH, and this is where the heat being added into the system, and an isothermal heat rejection process at TL, where the heat being rejected from the system at the temperature at low at TL. The Stirling cycle and Ericsson cycle. So what we can say here is that these two cycles are differ from the Carnot cycle in that the two isentropic processes are replaced by two constant volume regeneration process. This is in the Stirling cycle. Later on, you are going to see the TS diagram and PV diagram for both Stirling cycle and Ericsson cycle. So for Stirling cycle, we have the two constant volume regeneration, whereby for the Ericsson cycle we have two constant pressure regeneration. So that is the two main difference between the Stirling and the Ericsson cycle. Stirling is constant volume, and the Ericsson cycle we have the constant pressure regeneration. These are replacing the two isentropic processes that been highlighted in the earlier Carnot cycle. Right. For both cycles, Stirling and Ericsson, they utilize regeneration process, which is during the heat is transferred to a thermal energy. Okay, and thermal energy storage device, which is called the regenerator. Right, during one part of the cycle, and is transferred back to the working fluid during another part of the cycle. So this is being shown in this particular figure 926, where a regenerator, which is called a device that borrows energy from the working fluid. Right, this is the regenerator. Okay, the white color. It takes the heat from the working fluid that flows outside of the system. So the heat being transferred from the working fluid to the regenerator, where energy being transferred in, and at the same time energy being transferred back to the working fluid. Right. So as shown in the figure 27B, we are going to look at the slide in the next slide, which shows the temperature, entropy, and pressure volume diagram for Stirling cycle, which is made up again similar four totally reversible processes. Right. So process 1 and 2, where temperature is constant, where we have constant expansion, heat being added from external source, and 2 to 3, the volume, it is a constant regeneration. Okay, internal heat transfer from the working fluid to the regenerator, and 3 to 4, where the temperature is constant, compression, where heat rejection to the external sink, and 4 to 1, the volume is constant regeneration, internal heat transfer from regenerator back into the working fluid. This is clearly highlighted in this middle diagram, where we have a comparison between the Carnot cycle. We have already looked at the Carnot cycle, right? And then for today, we are going to focus on Stirling and Ericsson cycle. Okay, as you can see, for the Stirling cycle has been highlighted. Right, process from 1 to 2. This is at the constant heat temperature, where heat being added, and then from 2 to 3 we have constant volume for regeneration, and then process 3 to 4 where heat being expelled from removed from the system. We have temperature is constant, and from 4 to 1 go back to the earlier state where the volume is now constant. Alright. So later when you want to look at Ericsson, we can easily compare side by side between Carnot cycle, Stirling cycle, and the Ericsson cycle. Right. What happened is that the execution of the Stirling cycle, which requires rather innovative hardware. The actual Stirling cycle, including the original, that one that was patented by Sir Robert Stirling, which are heavy and bulky. Basically, it is a complicated system. And to spare all of you the complexities, the execution of the Stirling cycle in a closed system is explained with the help of this hypothetical engine shown here, right? So we have the execution of Stirling engine from state 1. Okay, this is the condition where heat being added at constant temperature, right? And then at state 2 where this is the condition where volume is now constant, and then where state 3 the where we have the condition over here, and when we have state 4 where the heat being expelled, we have the temperature at the same value. So you can try to imagine what happening in the execution of the Stirling cycles over here. So now we look into the Ericsson cycle. Okay, so the same figure 9.7, I extracted the Ericsson cycle PV diagram and TS diagram. Right, in this cycle, we can see the Ericsson cycle is very much like the Stirling cycle, except that instead of having constant volume processes, it is now replaced by the constant pressure processes. As you can see here, from 2 to 3, from state 2 to 3, we have constant pressure, and from 4 to 1, we have constant pressure as well. Similarly here, for the temperature, from 1 to 2, it is at constant temperature, and 3 to 4, it is at constant temperature as well. Compared to the Stirling engine, right? The only difference is that it is happen at the constant volume instead of constant pressure. And those are, I hope you can understand that those are the main difference between the Ericsson cycle and the Stirling cycle. Right. For Ericsson cycle, this schematic diagram shows a steady flow of Ericsson cycle, okay, where we have the isothermal compression. This is a compressor, isothermal compression, and expansion occurs in the which is occurs in the compressor and the turbine respectively. So you have the compressor over here, you have the turbine over here. Okay, so the heat being expelled and heat being generated into the system at the isothermal compression, right? At the same temperature. And counterflow heat exchangers serve as a regenerator in this particular system. We have a regenerator where the counterflow heat supply the system at the same temperature. So what happens is that hot and cold fluid stream enter the heat exchanger from opposite end, as we have shown in the earlier figure, and heat transfer take place between the two streams. Right? You can see back here the heat being generated, okay, from the regenerator, okay, and heat being transferred to and from the system. Right? And in this ideal case, the temperature difference between the two fluid streams does not exceed a differential amount at any point. And the cold fluid stream leaves the heat exchanger at the inlet temperature of the hot stream. Right? We can say that both the Stirling and Ericsson cycle are totally reversible. It can go back from process 1, 2, 3, 4, and then it goes back to 1. Okay, that what we say it is reversible. It can be reversed as is the Carnot cycle, similar to Carnot cycle. And thus, according to the Carnot principle, all of these cycles, Carnot, Stirling, and Ericsson must have the same thermal efficiency, right? When operating between the same temperature limit. So what we can say here, the zeta thermal efficiency for Stirling equal to thermal efficiency of Ericsson cycle, as well as equal to thermal efficiency of the Carnot cycle, which is equal to 1 minus temperature at the heat sink TL over temperature at the heat being added into the system, TH. And this is proof for the Carnot cycle in our earlier example 9.1, where we gone through the exercise example 9.1, where it shows how we prove the thermal efficiency for the Carnot cycle. And we can also prove the similar manner for both the Stirling and Ericsson cycle. Alright, let us look into an example where we have ideal gas as the working fluid. You have to show that the thermal efficiency of the Ericsson cycle is identical to the thermal efficiency of the Carnot cycle operating between the same limit. Remember, we are saying that between the same temperature limit of TL and TH. Right? As a solution, it is to be shown that the thermal efficiencies of a Carnot and Ericsson cycle are identical. We can analyze the heat is transferred to the working fluid isothermally from an external source, maybe a regenerator over there, at a temperature TH during the process from 1 to 2. And then the heat is rejected isothermally to an external sink at the temperature of TL during the process of 3, 4. Right? For reversible isothermal process, the heat transfer can be related to the entropy change. And we have the Q, the amount of heat being transferred per unit area, which is equal to the temperature times the entropy change. And the entropy change for an ideal gas during isothermal process can be rewritten as the corresponding equation. We have the delta S over here equal to the specific heat capacity at constant pressure log natural times to the temperature at the exit, but over temperature of the inlet minus the gas constant R log natural times the pressure at the exit over pressure of the inlet. Okay, so then since this is equal to 0, right, and you get only an expression of the pressure. Okay, so the heat input and heat output can be expressed as follows. So we have the heat input in the term of the entropy change times the temperature at the high heat added, right? And you can then input back the expression of the change of entropy that we have already worked out earlier, and we have this expression. Similarly, for the heat being expelled, the Q out, you can put TL times the entropy change at 4 and 3, right? Same here, you get the expression in terms of the pressure over P4 over P3. Then the thermal efficiency for the Ericsson cycle becomes as follows. We know that the thermal efficiency zeta TH for the Ericsson cycle equal to 1 minus Q out over Q in, right? And then you put all of the expression that we have already worked out and you cancel it out you will get the value of TL over TH, because P3 it is at Ericsson cycle, it is at this constant pressure. P3 equal to P4 and P1 equal to P2. That's why we can just cancel it out, all right, and then get the TL over TH, right? So that's how we prove that the Ericsson thermal efficiency is equal to this 1 minus TL over TH, similar to the Stirling cycle as well as the Carnot cycle. Right. So despite of the physical limitations and impracticalities associated with Stirling and Ericsson cycle, they give a strong message to design engineer, where we can say that regeneration can increase efficiency. It is no coincidence that the modern gas turbine engine and steam power plants make extensive use of regeneration. In fact, the Brayton cycle with intercooling, reheating, and regeneration that we are going to look later on today, which is used in large gas turbine power plant, and closely resembles the Ericsson cycle. All right. Okay. Now we want to move into a more interesting part, which is straightly related to the gas turbine engine, and we will look into the Brayton cycle. Okay, for Brayton cycle, ideal cycle for gas turbine engine, there are two types of cycle for gas turbine engine. One is an open cycle gas turbine engine. Okay, this type of gas turbine engine usually operate on an open cycle, as shown in figure 930 here, an open cycle gas turbine engine. Right? Why it is open cycle? Okay, because the flow is not being it is open, meaning that the fresh air coming in, and then fresh air coming out. The same fresh air, exhaust gases are not being bled back into the system, and that is a closed cycle. In this particular case, air coming into the compressor and then goes into the combustion chamber and goes to the turbine, and it is expelled to the atmosphere. All right, that is open. The air exhaust are not being bled back into the system. That's why we call it as a open cycle. So in this case, the high pressure air proceed into the combustion chamber, right? From the air that being compressed over here, high pressure being burned in the combustion chamber at the constant pressure, resulting the high temperature gases goes into the turbine, where they expand to the atmosphere. Right? This is where the work being done. Right? Compared to the open cycle, we have the closed cycle as shown in this model 931. Okay, so you can see here the air that being supplied by the heat exchanger go to the compressor, go to the heat exchanger, go to the turbine, and it is being flown back into the heat exchanger. Right, the same air coming back, and that's why we call it as the closed cycle. Right. Over here, compression and expansion processes remain the same, but combustion process is replaced by a constant pressure heat addition. Right? And the exhaust process is replaced by a constant pressure heat rejection to the ambient air. Q in, Q out. Okay? That's the main difference between the open cycle and the closed cycle. The ideal cycle that the working fluid undergoes in this closed loop is called the Brayton cycle, which is made up of 4 internally reversible process. Right? So you have process 1 to 2, okay, and 2 to 3, 3 to 4, and 4 to 1 back. This is 1 to 2 is isentropic compression. This is happening at the compressor. Okay, pressure increases. Okay, And then when you can see here, the pressure increases from 1 to 2, right? And then at constant pressure heat addition for 2 to 3, from 2 to 3, constant pressure heat addition, okay? And then this is happening at the combustion chamber, heat being added. Basically, combustion process occurs, temperature increases from T2 to T3 at constant pressure, 2 to 3 at constant pressure, but temperature increases. And then isentropic expansion in the turbine from 3 to 4, the temperature being reduced from the high temperature 3 to 4, right? This is happening the pressure isentropic expansion, okay? The pressure also being dropped from high pressure at the combustion chamber 3 to the turbine at 4, and then constant heat pressure rejection at the where at the nozzle 4 to 1 constant pressure heat rejection, okay, right? We can say that the thermal efficiency of a Brayton cycle is equal to the amount of work being done divided by the amount of heat being added. And this can also be translated into 1 over Q out over Q in. You want to find what is Q in, what is Q out, right? We can apply the conservation of energy to process 2 to 3, where we know the pressure is constant. There's no work at the combustion chamber. It is steady flow, and we can neglect changes in kinetic and potential energy. So we can say that the amount of energy into the system equal to the amount of energy out of the system, m dot 2 times H2 plus Q in equal to m dot 3 times H3. This is happening at process 2 and 3. So the conservation of mass will give the amount of mass flow rate into the system equal to the mass flow rate out of the system. So we know that m dot 2 and m dot 3 are the same, right? Okay, so we can just use the symbol m dot, okay, because 2 and 3 are the same. For constant specific heat, the heat added per unit mass flow is equal to the Q in to the system equal, which is the same as the mass flow rate times the enthalpy at 3 minus enthalpy at 2. Okay, so you can convert the enthalpy into the specific heat capacity CPT, right? You can write this down, and you can get the expression of the Q in, which is equal to specific heat capacity CP times the temperature difference between T3 and T2, and this is where the temperature being raised at the exit of the outlet of the compressor, right? And in the combustion chamber. Applying conservation of energy for the process 4.1, which also yields constant heat, specific heat. So you can conduct the same exercise for process 4.1 now, where heat being expelled. Okay, Q out equal to m dot times H4 minus H1. You use the same approach, you will get Q out equal to Cp times the temperature difference between 4 and 1, right? Hence, the thermal efficiency can be written as this expression, where we replace all the information that we have already got. We know Q out, we know Q in, we put inside the expression over here and rearrange everything. You will get the thermal efficiency in terms of the temperature at all stations. Temperature 1, temperature 2, temperature 3, as well as temperature 4. Okay? So you recall back for processes 1 and 2 and 3 and 4, which we know they are isentropic. Okay, so we can, for isentropic case 1 and 2, we can write the temperature relationship with the pressure ratio, with the value of the specific heat ratio of, in this case, is air. Okay, the gamma or K in this particular case, and for 3 to 4 station. Okay, so since we know that it is happening at constant pressure, right? So P3 equal to P2 and P4 equal to P1, right? Because it is assumed to be fully expanded. Okay, the pressure at the exit of the turbine is equal to the pressure of the atmosphere, the incoming air. We see that we can write the expression of the temperature as well, or T for T2 over T1 equal to T3 over T4, or the other way around, right? And now we can see that the Brayton cycle becomes only the expression of temperature T1 over T2. Since process 1 and 2 is isentropic, right? So we can write it in terms of the compression ratio R over there. Right? With the pressure ratio RP, which is equal to P2 over P1, we can rewritten the expression of thermal efficiency for Brayton cycle as the pressure ratio of the compressor. Okay? Right. Let us now look into the example. Probably it's best to go through an example so that you can appreciate more in terms of the application of Brayton cycle in a gas turbine power plant. Or in this particular example, we have a gas turbine power plant which operates on an ideal Brayton cycle. It has a pressure ratio of 8. So the R equal to 8 in this particular case. The gas temperature is given to be 300 Kelvin at the compressor inlet, and at the turbine inlet it is 1300 Kelvin, right? So T1 and T4 already given. Using the air standard assumptions, you have to determine the gas temperature at the exit of the compressor. You have to find T2. You also have to find T3. So the temperature at the turbine. Okay. Basically, you already have T1 and T4. You want to find T2 and T3. You have also to find the back work ratio and the thermal efficiency. So let us look into the solution. In this case, a power plant operating on ideal Brayton cycle is considered. The compressor and turbine exit temperature, back work ratio, and thermal efficiency are to be determined. What are the set of assumptions? First one, we assume it is a steady state operating condition. Okay, steady operating condition exists. And then the air standard assumptions are applicable. Then number 3, kinetic and potential energy changes are negligible. And finally, the variation of specific heat with temperature is to be considered in this case. All right. How does it look like in terms of TS diagram? So this figure 936, okay, shows the Brayton cycle for this particular case, example 96. So we have been given temperature of 300 at T1, and this is at the inlet, and at the turbine inlet it is at the 1300 Kelvin. This is where the temperature being raised from 2 to 3, and then we have to find what is the turbine exit temperature T4. Okay, we note that the component involved in the Brayton cycle are steady flow devices. Right. The air temperature and the compressor and the turbine exits are determined from the isentropic relations. Okay, using isentropic relation for compression of an ideal gas. Right, so we have the temperature T1 at 300 degrees Kelvin. We use a table of I believe it is a table ideal gas table. You can get H1 and PR1 Prandtl number. Okay, at station 1, and then we can have the expression over here. We know that PR1 equal to 8, and the pressure ratio P2 over P1. The pressure ratio is 8 and P2 over P1. And from the table of ideal gas, for air at 300 Kelvin, you can have the PR1 Prandtl number value for air at 300 Kelvin, 1.386. So you then get the temperature at 2 to be 550 Kelvin at the compressor exit. Alright. So from here, from the table, you look at PR2, which is 11.09, and you read the corresponding value of temperature and corresponding value of the enthalpy. Okay, this is the value of T2 and H2. Right? For process 3-4, isentropic expansion of an ideal gas, we given already T3 1300 Kelvin. This is the temperature at the exit of the combustion chamber going into the turbine. Okay, 1300 Kelvin. Right. So reading from the same table, ideal gas table, so you can get H3 and PR3 values, and using the same approach, because we know it is compression ratio is pressure ratio is 1 over 8, and for P4 over P3, and you put inside the value of PR3 over there, you will get the PR4 to be 41.36. Reading from the table, you will get T4 of 770 Kelvin. And you can then also get the value of enthalpy at station 4. This is the value at the turbine exit. Right. So now you need to find the back work ratio. The back work ratio that we need to find the work input to the compressor and the work output of the turbine. The work input of into the compressor is basically the enthalpy of station 2 minus enthalpy at station 1. So you have the values already. You get W compressor in to be 244.16 kilojoule per kilogram, and work output at the turbine to be 606.60 kilojoule per kilogram. Right? Putting the numbers in, you will get the value of back work ratio RBW to be 0.403. Basically, it is a 40.3% of the turbine work output is used just to drive the compressor. Okay. The next one is the thermal efficiency of the cycle. Is the ratio of the net work output to the total heat input. Put the numbers in already. You already have all the values. You will get Q in to be 851.62 kilojoule per kilogram, and the total work, the net work is 362.4 kilojoule per kilogram. Then you can work out the thermal efficiency of the gas turbine engine. uh, to become 42.6%. Right? The thermal efficiency could also be determined from the value here. Okay, 1 minus Q out over Q in. You can work out the Q out over there, and then you can put inside the numbers over here. So you can get another value which is 44.8%. Right. Let us look into, before we take a break, let us look into another example, example 9.7. This time around, we want to assume a compressor efficiency, given a compressor efficiency of 80%, and then a turbine efficiency of 85%. You have to determine the back work ratio, RWB, and then the thermal efficiency, zeta TH, and the turbine exit temperature of the gas turbine cycle, which already discussed in example 9.6 over there. The Brayton cycle discussed is in example 9.6 is reconsidered for specified turbine and compressor efficiencies. The back work ratio, thermal efficiency, and turbine exit temperature are to be determined. Right? So this is how it looks like for example 9.7, the TS diagram for example 9.7. In terms of the solution, the actual compressor work at turbine is no longer 100%. They gave us the value of the the efficiency for the compressor and efficiency for the turbine. So you can now use the value of the thermal efficiency for the compressor, which is 80%. You get the work from the compressor to become 305.20 kilojoule per kilogram. For the turbine, it is 85%, 0.85. You will get the work from the turbine 515.61 kilojoule per kilogram. So the back work ratio, RBW, for this case is that it is 0.592 or 59.2%. Right? So the compressor is now consuming 59.2% of the work produced by the turbine, which is up to 40%, 40.2%. So this increase is due to the irreversibilities that occur within the compressor as well as the turbine. The next part of the question, where in this case, the air leaves the compressor at a higher temperature compared to the earlier example 9.6 just now, and the enthalpy, right? So we have the new value for enthalpy, and you can get the work for the compressor 605.39, and the temperature for air that leave the compressor to become 598 Kelvin. Okay? So that leads us to the value for the Q in, the heat being added into the system, and the work that being done for the system. W out minus W in. Right. So then we can get the thermal efficiency to become 26.6%. So it is lower than the earlier example. Example 9.6 we have 42.6%. Now example 9.7 we have 26.6%. This is because of the irreversibilities that occur within the turbine and the compressor. And furthermore, the efficiency of the compressor and efficiency of the turbine is no longer ideal. It's no longer 100%. It is 80% and 85% respectively. Right? So these examples shows how sensitive the performance of gas turbine power plant, especially the compressor as well as the turbine. This is where the work being done. If it is ideal, it is 100%, but in actual case, it is not 100%. Okay. In fact, gas turbine efficiency did not reach competitive values until significant improvements were made in the design of gas turbine as well as the compressors. Alright. So the last part of the question asks us to find the air temperature at the turbine exit. We want to find T4. Okay. In this case, is T4A. The air temperature at the turbine exit can be determined from energy balance on the turbine. Okay, same approach that we used before. We get the work from the turbine to become 880.36 kilojoule per kilogram, and you read from table A17, you can get value of T4 to become 850. Note that the temperature at turbine exit is considerably higher than that the compressor exit 598. So you can see here, right, which suggests the use of regeneration to reduce the fuel cost. Okay, so this is where this is just a snapshot of the how you get the value from the table, table A17, right? So you have H. You already have H1 866.08 and at the temperature of 840 over here. You also have 860 Kelvin, but you want to find what is the value of the temperature at 80.37 kilojoule per kilogram enthalpy. It is just sit between here, so you have to do interpolation to get what is the corresponding value of the temperature. Alright, so the value of the corresponding temperature is basically 853. If you work out this using this formula, you can get the value in between.